All right, so I'd like to talk about today three-dimensional scenarios. And so yesterday we talked about, or the day before, whatever that was, last lesson was, um, what happens if a line and a line exist in two dimensions, two-dimensional space, and what are the possible ways that these two guys can basically intersect. All right, we're talking about solutions to equations here. All right. So now, if we end up putting a line in 3D, in 3D, we could have various different outcomes, right? So let's go ahead and draw our coordinate planes here. So remember, our coordinate plane in 3D looks like this, right? So I'll put one over here as well, and here. Oops. Okay, so you would imagine that an infinite solution line basically is where one line is equal to the other line. Okay? And a one solution would be where one line crosses the other line and they intersect. I've got this looking like it's a right angle. It doesn't necessarily have to be a right angle, though. And then finally, we've got no solutions where you've got two lines that are essentially maybe parallel sitting here. Okay? There's actually one other way, right? In two dimensions, you could have a line that kind of goes, in three dimensions, you could have another line that sort of goes behind these two lines, right? But they're not necessarily parallel either. Okay? And so what we're going to do is we're going to try and figure out a sort of a system here where I've given two lines. Remember, by the way, three-dimensional lines are only given in vector equations, not scalars. So when I'm looking at my line, the only way I can receive the information is through a vector equation. So this is going to simplify everything a little bit, okay? And so basically, if the lines are parallel, right, then the slope 1 is parallel. Sorry, I'm saying that incorrect. If there's infinite solutions, then one line is equal to the other line. Then basically what that means is the two slopes are parallel, so the ratio of the components of the slope vectors are equal, okay? And furthermore, a point on one line is a solution to the other. And so let me write that down. So in order for you to have infinite solutions, M1 is parallel to M2. And hopefully, I'm hoping that you now just know what that means. Basically, if M1 is parallel to M2, this is M1, because that's line 1. This is M2, that's line 2. And so therefore, this is the slope vector. They must be parallel. How do they're parallel? That would mean that 2 divided by 1 is equal to 1 divided by 5, which is equal to 3 divided by 5. Okay? Well, that's not the case in this scenario. So we obviously don't have this situation. Okay? But here we've got the lines that are parallel. Okay? But furthermore, point 1 is a solution to line 2, okay? Basically what that means is I can take point 1, 7, 2, 6, and I could place it here, 7, 2, 6, okay? And then what I can do is I can write out my x component, which would be 7 equals 3 plus 1s. I could write out my y component, which would be 2, right, because I'm doing 7, 2, negative 6. 2 equals 9 plus 5s. And I could do it again for the z component. And then I solve for s in all three of those. If I get the same s in all three cases, then what that means is point 1 is on line 2. And if furthermore their slopes were parallel, then basically what it means is you're looking at two equations where the lines themselves, they're actually just the same line. Okay? So that would be how that one works. I don't think I have an example of that in this because it's very similar to an example we did back up here, right? Wherever that was. Okay? I don't know. I can run through one of those by request though. So anyway, let's go with one solution. Well, in a one solution scenario, we know that M1 is not parallel to M2. Okay. And when we have a one solution, okay, what we end up getting is the z components are equivalent. Okay. The z components are equivalent. And I'm going to put a little star there because you might be thinking to yourself, I don't really know what that means. I'm going to run through that in just a moment as the examples unfold. Okay? So basically now over here, right? Over here, okay? If there is no solution, we have two possibilities, all right? Two possibilities. So I'd like to break this into two little subcategories, all right? One where M1 is parallel to M2, and one where M1 is not parallel to M2. In this case, then P1 is not a solution to line 2, and in this case, the z components are not equivalent. And so basically you have four scenarios here, right? Notice there's two scenarios here. Now we're only ever talking about two lines. I don't want you to get confused because I've got three lines in this diagram. Basically, you kind of pretend like I've got two scenarios. Either they're parallel, like this line and this line, or they're what's called skew, where you've got one line here and another line there, and then you can kind of ignore this line for the moment, all right? And that would, in either one of those cases, it would fall under the no solution category, or the one solution category. There's only one way of getting that, and infinite solutions, there's only one way of getting that. So I'm hoping you're now kind of seeing the way that this is organized, okay? So now let's break it down into what I've written in blue here. If you look closely at this is now a problem-solving approach, the way that I've written it. So you're basically asked, find the solutions to the following system. The answer is either there's infinite solutions, there's one solution, or there's no solution, okay? And so you might say, well, how am I going to do that? First thing you do is you test to see if your slopes are parallel. If your slopes are parallel, then you either have, this case here or that case there. And so now, once you've seen that your slopes are parallel, you test one point in the other line. If it's a solution, then you have this. If it's not a solution, then you have parallel lines, okay? So the answer here would be you have the same line. Or I guess what I'm going to do is line 1 is equal to line 2. In this one, you would say, therefore, line 1 is parallel to line 2. And okay, so just a quick run through on that again. You first test to see if the slopes are parallel. If they are, you put a point into from one of the lines into the other and check to see if it's a solution. If it is a solution, you have the same. You're looking at the two equations of the same line, two different equations. If it is not a solution, then you are looking at two lines that are parallel. Okay, and that's all. Now let's go back up to these two possibilities here and here. So remember, you're looking for solutions. So you first check to see that the slopes are parallel. If you discover that the slopes are not parallel, you either have one solution or you have this scenario where you've got a line and another line, but they don't touch, but they're also not parallel. This is, by the way, called skew lines. And so you would say, therefore, line 1 and line 2 are skew. All right. Whereas over here, you would say that therefore, bang, XYZ is the point of intersection. And you have to find these numbers. Is the intersection, or the solution, or you could even say, is the solution. All right. So then that leaves this little asterisk here. The z components are equivalent or the z components are not equivalent. Okay, and so basically you've got this, right? So you find that your slopes are not parallel, and so then you have to do this thing, and the final conclusion of that is what I just said there. Okay, so question is what do I mean by z components are equivalent or are not equivalent? Okay, well, I'm about to run through this example here. Okay, so find the solutions to the following system. These are vector equations. So the question are the slopes parallel? First thing. Okay, so is 2 over 1 equal to 1 over 5? No. And it's definitely also not equal to negative 3 over 5. All right. Now remember, in order for you to be non-parallel, so therefore, line 1 is not parallel to line 2. So therefore, I know automatically I'm here or here. I don't know which one yet. Let me go back. In order for you to not be parallel, all three of these things, it's not that all three of them have to be unequal. Just one of them has to be not equal to the other two, or all three can be not equal. That would be non-parallel. Okay, so now that that's the case, what do? I actually take the x and the y components, okay? And then I take the z component, and I write it far away over here, all right? My x component is 7 plus 2t, and it's 3 plus s. Oh, I'm going to write an m again. I'm going to always get rid of my s's and write m's because I don't like s's because they look like 5s. So I'm going to go through this quickly now. So remember, in order to get your x component, it's 7 plus 2t and 3 plus 1m, okay? In order to get your y component, it should be 2 plus t, and my y component would be 9 plus 5m, okay? Hopefully I've gotten that all done correctly. I've got 1s and 5s. I've got 2s and 1s, 7s and 3s, and 9 and 5. There it is. Okay. And then I'm going to get my z component over here. My z components are negative 6 plus negative 3t. I mess these up all the time, actually. My z component is negative 6 plus a negative 3t, or minus 3t, I guess is what I'm going to do. Negative 6 minus 3t. And my Z component here is 13 plus 5m. All right. So now the question is, are the Z components equivalent? All right. So what I'm going to do is I'm just going to tell you exactly what I'm going to do. And then from here, you can pause the video, do it yourself, or you can see what's going on. Basically, what I'm going to do is I'm going to solve for T and M in here, then take those T and M's and put them here. If I get these two Z components that are equivalent, then I had this scenario. If I get those two Z components that are not equivalent, then I had this scenario. Okay. So let's go ahead and solve for T and M over here. All right. So I'm basically just going to take these two equations here. And in order to do this, maybe I'll solve for T in this bottom one, right? And so I'm going to maybe, I don't know, subtract the 2 over, and I'm going to get in the y equation, T equals, subtract 2, I'm going to get 7 plus 5m, right? And now in my x equation, I'm going to get 7 plus 2t, but remember t is 7 plus 5m, equals 3 plus m. And now I'm going to get 7 plus 14 plus 10m equals 3 plus m. I'm going to maybe isolate for m here. And so I'll pass my numbers to one side and my m's to the other. And I'm getting a 9m equals, what's 3? 7 is 14. So 14 is 21. 21 minus 3 is 18. Is that right? Is that a negative 18? Passing it over there, and I'm getting m is a negative 2. Oh, that's nice. It worked out. And then what I'm going to do is I'm going to take this and I'm going to write 7 plus 5 times negative 2. And I'm going to discover that t is equal to 7 plus 5 plus negative 10. I'm getting a negative 3. Hopefully I got that right. And now the question is, so I know what m is, I know what t is. You're always going to get a solution to these, by the way. You're almost always going to get a solution to these. Okay? As a matter of fact, I think you will always get a solution to this part if it's true that your slopes are non-parallel. Okay? You would get no solutions here possibly, but if your slopes are parallel. But remember, if your slopes are parallel, you wouldn't even be doing what I'm doing right now. Okay? And so now what you do is you take this m of negative 2 and this t of negative 3, and you go ahead and you throw it in over here. So look at this. Negative 6 minus 3 times t. Well, t is negative 3. And 13 plus 5, m. m is negative 2. And there you go. You now look to see if your sides of your two equation are the same, right? So what's a negative 6 plus 9? Well, it's 3. What's a 13 minus 10? It's 3. Oh, look at that. They are the same. Look, I got 3 equals 3. So therefore, what that means is that the z components are equivalent, and therefore x, y, z is the solution. So I have a single point solution, and there it is right there. But I need to write it down. The solution is something, comma, something, comma, 3. 3, this z is equal to 3, as you notice. But now I have to figure out the y components and the x component, right? So in order to get the x component and the y component, okay, what I'm going to do is I'm just going to take the 7 plus 2t and the 2 plus t, and I'm just going to write that down. So 7 plus 2t, but remember that t in this example happens to be negative 3. And I'm going to get 2 plus t, or 2 plus a negative 3. And as it turns out, my y is 1. my x is 1, and my my y is -1. And so it's 1, -1, and 3. That's the solution to this question, all right, or this system of two lines. Basically means if I graph this line and I graph that line, they will both go through this point. And that's the only point that they will both go through. And so therefore it's the intersection, and it's also known as the solution to the system. What would happen? So I would have known here, I would have gone here. This would have been the answer over here where I'm pointing the mouse now. If I got something like 3 is equal to like 7 down here, right? Then I would have said, the z components are not equivalent. Therefore, the two lines actually don't touch, but they're not parallel because I've already verified that they're not parallel, okay? So just a quick thing there. The overall approach is you first test for parallelness of the slopes. If you determine that they're not parallel, then you set up the x and the y components. You solve for the two parameters. You take the two parameters, you plug it into the z components. If you get the same number, then they are the two lines intersect at a point. If you don't get the same number, the lines are skew. And then if they do, you can find that point by doing this little process right in this area. Okay? Now, determine the intersection of the following two systems. If there is no intersection, determine the distance between the lines. Okay? The distance between the lines formula is this. Okay? So in this scenario, I think we actually have no solution. So I'm going to show you. I think the reason why I wrote this question so that we could use this distance between two lines formula. And so I'll show you how to use this. First of all, what I want to do is I want to figure out, do they intersect? I think the answer is no, but we want to verify it. First of all, we always check the slopes. So I'm going to get a 1 over 2. Does it equal to 2 over -1? Sure, it does not equal, so therefore they are not parallel. I can even write down that it doesn't equal 3 over 1. But line 1 is not parallel. Is not parallel to line 2. Okay? That's that. So when we've established they are not parallel, what we do is we set up the x and the y components. Okay, so I'm going to write maybe in blue, x equals 5 plus t, which equals 2 plus 2m. And again, I'm going to change this to an m. And my y component is -4 plus 2t. And my y component here is 0 minus m. Okay? And now what I'm going to do is I'm going to solve for t and m in these two things, and then I'm going to plug the solution into the z components. And we'll see, I think in this example, we're going to see that the z components are not equivalent. But let's try it out. Here it looks like I've got m pretty close to being isolated, so I'm going to go ahead and just write down the y equation is equal to m equals a -2t plus 4. I just took the y equation and solved for m there. Okay. Now I'm going to take the x equation and I'm going to write 5 plus t equals 2 plus 2m, but remember m is 2t plus 4. And now it looks like I should be able to solve for t in this equation. So let me make sure I just try not to make any mistakes here. Whoops. Let's go ahead and change that to a minus. So I'm getting a minus 4t, and I'm getting a plus 8. Okay, 8 and 2 is 10. There's a positive 10, and that's a 5. So that's going to be a -5 equals -5. Is that right? 5t, it appears that t equals 1. Okay? All right, if t equals 1, then m equals 2, because negative 2 times 1 plus 4 equals 2. So m equals 2 and t equals 1. All right? So now I'm going to check the z component. All right? And I'm going to save some space because I know this isn't going to work out. So I'm going to go negative 2 plus 3t, right? And my z component for my line 2 is 1 plus m. Okay? So remember, this stuff is always coming from, this is the x component for line 1, the y component for line 1, the z component for line 1. This is the x component for line 2, the y component for line 2, and the z component for line 2. Now I know that m is 2 and t is 1, so I'm going to write this down. Negative 2 plus 3 times 1 equals 1 plus 2. Well, 1 plus 2 is always 3, and negative 2 plus 3 is 1. Well, 1 does not equal 3, and so therefore the line 1 and line 1 and line 2 are skew. That's the answer. But then it goes on to say, well, if there is no intersection, meaning if they are skew or parallel, then determine the distance between the two lines. Okay, well, in order to find the distance between two lines, I'm going to go ahead and use this formula here, right? It's P1, P2 dotted with M1 cross M2, and that's absolute value divided by the magnitude of M1 cross M2, okay? And so I guess I don't need to rewrite this distance formula over there. It's written right there. So I'm going to save myself some space and get rid of that. So let's see what we've got. So the anatomy of these lines are as such. This is basically P1. This is P2. This is M1, and this is M2, okay? So P1, P2 is basically a vector that joins these 2 points, okay? Now note, these are vectors, not points, but these are vectors that point to a point, okay? And so what we're going to use is the point version of these 2 vectors. So remember, in order to find P1, P2, I take 2 minus 5, 0 minus negative 4, and 1 minus a negative 2, and that's my vector, and it's a vector P1, P2, okay? So I'm going to write that over here. The vector P1, P2 is 2 minus 5 is its x component. 0 minus a negative 4 is its y component. And 1 minus a negative 2 is its z component. And so let's try and not make a mistake here. We got a negative 3. This looks to be a 4, and this is looking to be a 3. So P1, P2 is that, all right? Now, so that's that part of the equation. Now I got to dot that with M1 cross M2, okay? And I need also M1 cross M2 down here. So let me go ahead and take M1 cross M2. By the way, there's something here that I want y'all to know. Here is what's called a triple scalar product, okay? And what we're going to do is... Okay, sorry, somebody was at the door. I just paused the video. Let's see, where am I at here? Back where I was talking about P1, P2 dot M1 cross M2. This is what is known as the triple scalar product, okay? And the question is what do I do? Do I do the dot product before the cross product? Or do I do the cross product before the dot product? And the answer is you do the cross product first. And the reason is because remember, if I do a dot product, I end up with a scalar or a non-vector, okay? And that scalar cannot be crossed into a vector because the cross product requires two vectors as inputs. And on the contrary, if I do a cross product, the result is a vector. And so therefore, the vector that is the cross product of M1, M2 can be dotted with P1, P2, okay? So I just wanted to let you know, please be aware, always cross before you dot if you see them in a scenario like this. And then these symbols here are actually absolute value symbols. They're not magnitude symbols. And just to explain why, because now imagine what's going to happen here. I've got M1 cross M2, so that's a vector. Now I've got a vector, and I'm going to dot it with another vector. And so what's the result? The final result would be a scalar, okay? And so, therefore, these, if I have, bars around a number, just a scalar, then they are absolute value. Whereas down here, these bars are magnitude bars, okay? Because this is going to be a vector, the result, and then basically if I put bars around a vector, that means take a magnitude. If I put bars around a scalar, that means take the absolute value, okay? So therefore, we've dissected that formula pretty effectively, I hope there. And so we are now looking at the idea we now need to take M1 cross M2. So I need it in two locations here. So I'm just going to go ahead and do that. So therefore, M1 cross M2 is going to be like this. So I'm going to do X, Y, Z, X, Y, Z. I'm just going to go with my standard cross product that's taught to us in the textbook here. All right. So I've got 2, negative 1, 1, 2, negative 1, 1. All right. So now, in order to get the X component, I take these guys and these guys, right? And so it's basically to get the X component. This is let me put the X component is 2 times 1, or 2, minus 3 times a negative 1, or a negative 3. My Y component, whoops, I don't know why I'm writing Y there. My Y component is going to use these guys here. So it's 3 times 2, or 6, minus 1 times 1, or 1. And my Z component, I think you maybe can see, is going to use 1 times negative 1 and 2 times 2. All right. So therefore, my Z component is going to be a negative 1 minus 4. And so therefore, I'm looking at 2 plus 3, or 5, comma, what's 6 minus 1 is 5, and what's a negative 1? Oh, look at that, negative 5. Hopefully I did that right. So this is M1 cross M2 vector. Okay, that's what we're looking at. I guess I don't need those vector symbols. All right, so I have M1, M2, or I have M1 cross M2. I've got P1, P2. Now I need to dot product those guys. And so to get my distance, it's just equal to the dot product of these two vectors here and here. So it's 5 times negative 3. All right, so 5 times negative 3, or negative 15, Remember, the dot product, you multiply each component and add them. And then it's 5 times 4, which is 20. And then it's negative 5 times 3, which is negative 15. And so we're looking at around 10, negative 10. And it's absolute value, right? So it's actually a positive 10. And then over here on the bottom, I'm going to be taking the magnitude of m1 cross m2. So it's 5 squared plus 5 squared plus negative 5 squared. And so it looks like I'm getting about the root of 75, okay? And that is the distance between those two lines, okay? Yeah, basically that's what that is, all right? All right. Let's do one last question here. Is this the same question? Negative, this is 5. Oh, shoot, it's the same question. Well, let's see. Let me build a scenario where, let's see, let's do a parallel one where maybe we've got two lines that are separate like this. Or maybe we've got the same line. I don't know. I'm just going to make up a parallel one, okay? So watch this. I'm going to change this here to, I don't know why I have the same question written here. So let me go line 1 and line 2. So line 1 is x, y, z. Line 2 is x, y, z. And let's just say that this is like 1, 1, 1, okay? And this is like 2, 1, 0. And I'm going to add a parameter of t and a parameter of m. And I'm going to make my slopes parallel, okay? So I'm going to say that this is like 2, 1, 5. And then I'm going to say that this is 4, 2, 10. All right? I just built it so that they were parallel with each other. All right, and I'll even throw negatives in there. I'll throw a negative there, and a negative there. I don't know if you can see those negatives. It's a negative 10, negative 4, and a negative 1. So now, the question is, determine the intersection of the following system. If there's no intersection, determine the distance between the lines, okay? And so, therefore, I'm going to say we've got, well, first I check for parallel. Is 2 over negative 4 equal to negative 1 over 2? Oh, sure it is, actually. Is it also equal to 5 over negative 10? It is. And so, therefore, line 1 is parallel to line 2 for the time being. Now, the question is, are they the same exact line or are they not the same exact line? So what you do is you plug point 1 in here as a solution, and you see if it is a solution, okay? And so I'm going to basically take the parametric equation for line 2, and I'm going to say x, y, z, and I'm going to make x, each of these 1, okay? And that corresponds to that, right? And then I'm going to build the parametric equations over here, okay? You might be saying, well, what am I doing? Remember, up here, let me just quickly go up here. Remember, if the things are parallel, I either have P1 is a solution or is not a solution. Sorry, this is, okay, so what I'm going to do is I'm going to try that. So I'm going to take P1, which is 1, 1, 1, and I'm going to plug it into line 2. And so the x component is 2 plus a negative 4m, or 2 minus 4m. And if I solve for m here, I'll subtract 2 and divide by negative 4, and I'm going to get m equals a negative 1 over negative 4. Now I'm going to get the y component is 1 plus 2m. So 1 plus 2m. All right, what's the answer here? Well, it's 1 minus 1. It's 0. So we get m equals 0. I don't even need to test the z components because in order for it to be a solution, I need to get an m of the same value all 3 times. So I can automatically now therefore conclude that these are not the same line. So line 1 is not equal to line 2. But as stated before, line 1 is parallel to line 2. And as per the question, it says, if they do not intersect, I have to determine the distance between the two lines, okay? So therefore, the distance between the two lines, I'm going to take P1, P2 vector, all right? And so therefore, the P1, P2 vector is going to be 2 minus 1, 1 minus 1, and 0 minus 1. Well, 2 minus 1 is 1. And then this is 0, negative 1. So it's 1, 0, negative 1. Then I'm going to take, and I'm going to try and find M1 cross M2. Okay? I'll do it with my x, y's, and z's. All right? So that's x, y, z, x, y, z, and I'm getting a negative 2. That's a positive 2. I'm looking right here now at my slopes. So it's 2, 1, 5, 2, negative 1, 5, 2, negative 1, 5. And then I'm going to get negative 4, 2, negative 10, negative 4, 2, negative 10. Okay. Now to get my x component, it's 1 times negative 10, or 10, minus 2 times 5, which is 10. Oh, that's 0. How nice is that? And, oh yeah, this makes perfect sense, actually. Look, what's 5 times 4? Negative 4 is 20. And minus a positive 20. Oh, so I get a 0 again. And then I've got my z component is 4 minus 4, or 0 again. Oh, the 0, 0, 0 vector. That makes actually perfect sense, because why is M1 cross M2 0, 0, 0? Because they're parallel. I forgot about that little rule. It's been a long time. So I should have known that. And, the reason why they're parallel, because remember, the cross product definition asks you to do the sine of the angle between them. These are parallel. We already established that they're parallel. So what's the angle between two vectors? It's the angle between two vectors that are parallel is 0. And so therefore, what is the sine of 0? It's 0. And so therefore, the magnitude of this vector is 0. So it's the 0, 0, 0 vector. Okay. And let's see the distance formula here. So yeah, we're going to have a bit of an issue, because I've got the 0, 0, 0 vector right here. Okay. And so it's going to be tough to find the distance between these two guys. Does this come up? I just made this question up. This might actually come up. So let me show you a different a different technique for this one. I'm gonna have to go get that. Let me pause this. All right, so I thought about this, and I think there's no questions in the textbook that end up asking you to find the distance between two parallel lines, though it's actually not all that difficult. Okay, um, so I'm gonna explain how to do it, but I won't actually go through the math. By the way, if I were to apply this, I didn't mention all this. I didn't finish this question, but if the distance, if I went ahead and just plugged all this information in, I would get 0/0, and you'd be thinking, well, wait a minute, what is the distance, right? So let's take a look at this, right? I've got basically two lines, right? Like this, all right? And what I'm going to be doing here is, I want to basically find the distance between these two lines. Well, the distance is the same here as it is here, okay? And so essentially, but what I currently have is, well, I have the slope, okay, of each of these lines, and then I have some points, right? But one of the points could be like over here. Oops. And let's say the other point is over here, all right? And so basically, the question is, what you would end up actually doing, right, is you would end up basically creating a perpendicular line, okay, here to that slope, all right, that ends up, and you'd have to somehow get it to intersect over there, all right? And you would then draw a vector between these two here, and you would take this vector and you would project it onto that other, this one here, this projection, and that projection there would be the distance between these two lines, okay? The thing is now that I'm thinking about it, our textbook doesn't ask us to do that, and I've never asked a question on a test, right? Like, so I'm not necessarily going to go through the math there, okay? And so yeah, that's how you would end up doing something like that. So in this case, we would just conclude that they are parallel. All right. All right. So that's basically intersections of lines in 3 dimensions. All right. So run through a few examples of those. There will almost certainly be a test question involving intersections of lines in 3D, plus a few maybe distances, things like that.